At this point, we have given an axiomatic definition of the Lebesgue integral for non-negative extended Borel functions, stated its properties that will only be proved next week. They are axioms for us for the time being. We used this axiomatic definition for non-negative extended Borel function. We used it to define the integral of non-extended Borel functions in general. And we saw some properties that would follow from that definition. We saw that the expectation of a random variable is nothing but the integral of that random variable with respect to the probability measure. And now in this video lecture, we're going to further develop from the definition that we gave in the previous video lecture and establish some general properties of the Lebesgue integral. First, a very simple definition. What does it mean to integrate First, a very simple definition. What does it mean to integrate an extended Borel function on just a measurable set of the measure space? Well, this is by definition replace the function to be integrated by a function which is 0 outside the set and which coincides with f on this set, which is exactly represented by this function here. It's function f multiplied by the function indicator of the set B. So we integrate that with respect to the original measure mu on the measure space omega. This is the definition. And together with this definition, we are also stating here a little proposition which says this is the same as the Lebesgue integral of the original function f with respect to a different measure, which is not the measure b, but rather not the measure mu, but rather the restriction of the measure mu to this set B. So the definition, there is nothing to discuss. It should be clear what the definition is, and hopefully also what's the motivation for defining it this way. And why these two are equal is a very interesting and typical argument in the theory of integration. We're going to see part of the proof now and part of the proof next week as a particular case of a standard procedure to prove properties involving integrals. And this standard procedure, it consists in the following. It consists in first assuming that f equals the indicator of A for some A in the original sigma algebra of the underlying measure space. So it is, we assume first this, and then we prove it for this function, and this is what we're going to do today. And next week we're going to see how can we bootstrap for functions of this type, which are the simplest possible type of function. It only takes values 0 and 1. How to easily bootstrap properties that hold for binary functions of this type to general functions. Today we're going to do just a function which is the indicator function of a given set. And in that case, what we need to prove is that this integral equals this integral. And, well, how can we prove that? We just expand what each of these integrals would give. So the first one here, what is it? What is the integral over omega of f? And I'm substituting here, instead of f, the indicator function of a set A times the indicator function of a set B with respect to a measure mu. So what is the indicator? What is the product of two indicator functions? I'll let you think about it. The product of two indicator functions is again a function that only takes value 0 and 1. which means it's necessarily an indicator function, and it's an indicator of which set? Well, the set A intersection B with respect to the measure mu. And now we use the property that integral is a unitary operator, meaning when you take the integral of an indicator function, what you get is exactly mu of A intersection B. And now all we need to do is expand the second integral and see that we get exactly the same thing. And how do we expand the second integral? Well, it's the integral over omega of this function f, which we are assuming is the indicator of some event A, against the measure, not mu, but rather the restriction of mu to the set B. We can see the definition of restriction of a measure in chapter 2 of the lecture notes. And, well, by, again, property of what is the integral of an indicator function, this will be just the measure of that function, the measure mu restricted to B of this set A. And now we go by the definition. What's the definition of the restriction measure? Well, the restriction measure is a measure that assigns to every set A the measure of A intersection B. And now we see that these two are indeed equal. This concludes the proof. Now, to conclude the first part of this video lecture, a very familiar theorem we have been using, which says how can we compute an integral of a function if we know the antiderivative of that function, which is called the fundamental theorem of calculus. And, well, it also holds for the Lebesgue integral. This is, of course, good news. We don't want to throw away completely the integral we had been using before. We just want to replace it by a better one. And so in practice, if we want to compute an integral, this is how we compute it. And this dx here, conveniently, is just a way to denote the Lebesgue measure. So the Lebesgue measure, it can be sometimes denoted m, but sometimes it can be denoted dx, which helps this expression here look more familiar to us. Now, how do we prove this theorem? I'm not going to write the entire proof of this theorem because this is not the topic of this course, of this module. We already know how to prove the fundamental theorem of calculus for the Riemann integral. And which properties of the Riemann integral do we use when we prove the fundamental theorem of calculus? We use the following. We use that if a function g is bounded between two constants, then when we integrate on this interval that goes from a to b, the function g, this is between the same two constants. We use that, and we use properties of continuous functions, not properties of the integral, in fact. And this has nothing to do with an integral. It says if g is continuous on AB, M is the infimum over AB of this function g, M prime we define as the supremum, again on this interval E of the function g. Then for every L between M and M prime, there exists some C in AB such that G of C equals L. Let's make a picture of what is being said here just to be clear. We have an interval AB, closed interval. G is a continuous function. And if we look at the graph of G, then G takes a maximum value, a minimum value, and for every value between the maximum and the minimum, there will be at least one point C where G takes that value. This is the only properties that are used when proving the fundamental theorem of calculus. These properties, they hold for the Riemann integral. They also hold for the first property. It holds for both Riemann integral and Lebesgue integral. And the second property is a property of continuous functions, not a property of integrals. So this proves the fundamental theorem of calculus.